Welcome to G Fun Facts Online. Today, we journey into the heart of the atom, to a place where the rules we thought were set in stone are being dramatically rewritten. For nearly a century, our understanding of nuclear physics has been anchored by a concept known as magic numbers, specific counts of protons and neutrons that grant atomic nuclei an extraordinary level of stability. But a wave of recent discoveries is showing us that this magic can be fleeting, that these numbers can vanish in some atoms, while entirely new ones appear in others. This isn't just a tweak to an old theory. It's a paradigm shift that redefines the fundamental forces that hold our universe together and guides our search for the very limits of matter. So, what are these magic numbers? Why are they breaking down? And what new rules are emerging from the atomic frontier? Let's dive in. In the world of nuclear physics, the term magic number refers to a specific quantity of protons or neutrons that leads to a complete and therefore exceptionally stable nuclear shell. Think of it like the electron shells you learned about in chemistry. Just as noble gases like neon or argon are chemically inert because their outer electron shells are full, certain atomic nuclei are incredibly stable because their proton or neutron shells are full. The 7 most widely recognized magic numbers are 2, 8, 20, 28, 50, 82, and 126. A nucleus with a magic number of protons or a magic number of neutrons is called magic, but a nucleus that has magic numbers of both is called doubly magic, and these are the titans of stability in the atomic world. Famous examples include helium-4 with 2 protons and 2 neutrons, OXY-GEN-16 with 8 of each, and the heavyweight champion Lead-208 with 82 protons and 126 neutrons. These nuclei have a higher binding energy per nucleon, meaning it takes more energy to tear them apart, making them highly resistant to nuclear decay. This magical stability was first noticed in experimental data back in the 1930s, but it wasn't until the late 1940s that physicists Maria Goeppert-Mayer and J. Hans D. Jensen independently figured out why. They developed the nuclear shell model, which proposed that protons and neutrons, collectively called nucleons, occupy distinct energy levels or shells inside the nucleus. When a shell is filled, you get a magic number and a super stable configuration. Their work was so foundational that it earned them a share of the 1963 Nobel Prize in Physics. The name magic number itself is said to have come from the physicist Eugene Wigner, who, upon reviewing the evidence, found the pattern of stability so striking it seemed a little like magic. For over half a century, this model has been the guiding light for physicists, successfully predicting the properties of countless nuclei and forming the basis for our entire understanding of nuclear structure. But what happens when you wander far away from the well-behaved, stable nuclei we find on Earth? What happens when you venture into the wildlands of the nuclear chart, to the so-called exotic nuclei? These are short-lived isotopes with a severe imbalance of protons and neutrons. It's here, at the extremes of existence, that the magic starts to fade. The most dramatic example of this vanishing act involves the nucleus of oxygen-28. With 8 protons, a classic magic number, and 20 neutrons, another classic magic number, oxygen-28 was predicted for decades to be a doubly magic, ultra-stable nucleus. It was a poster child for the shell model. But in a groundbreaking experiment at the Riken radioactive isotope beam factory in Japan, scientists finally managed to create it. And the result was stunning. Oxygen-28 wasn't stable at all. In fact, it was so unstable, it decayed almost instantly, disintegrating in a mere zeptosecond. That's a trillionth of a billionth of a second. It immediately shed 4 of its neutrons to become the more stable oxygen-24. This discovery was a bombshell. It meant that the magic number 20 for neutrons, a rule that holds true for stable nuclei, simply disappears in the neutron-rich environment of oxygen-28. The magic was gone. And this wasn't an isolated incident. In a region of the nuclear chart known as the Island of Inversion, scientists found that other magic numbers were also losing their power. In neutron-rich isotopes like magnesium-32 and silicon-42, the magic numbers of 20 and 28 respectively weakened significantly. Instead of having the perfectly spherical shapes characteristic of magic nuclei, these isotopes were found to be deformed, a clear sign that the expected shell closures weren't happening. More evidence piled up from facilities like CERN's ISOLD. There, researchers precisely measured the size of potassium nuclei and found that for potassium-51, there was no evidence of the expected shell closure at neutron number 32. A closed shell should cause the nucleus to suddenly shrink, but the potassium nucleus just kept growing. It became clear that the nuclear shell structure wasn't a static, universal set of rules. It's a dynamic, evolving landscape where the rules of stability can bend and break under extreme conditions. But as the old magic fades in some corners of the atomic world, a new kind of magic is beginning to appear. The vanishing of old magic numbers isn't the whole story. In their place, scientists are discovering entirely new numbers of protons and neutrons that create unexpected islands of stability, forcing a complete revision of the nuclear spellbook. One of the most significant discoveries has been the emergence of new magic numbers for neutrons at 32 and 34. This was confirmed in experiments looking at the exotic isotope calcium-54, which has 20 protons and 34 neutrons. At both Riken in Japan and CERN in Switzerland, researchers measured the energy of calcium-54's first excited state. In a magic nucleus, the energy gap between the filled shell and the next empty one is large, so it takes a lot of energy to excite it. They found that calcium-54 had a relatively high excitation energy, a clear signature that 34 is indeed a new magic number for neutrons in this system. This confirmed theoretical predictions made over a decade earlier and provided the first concrete proof of a new magic number in a very exotic nucleus. The list of new neutron magic numbers has since grown, with studies identifying 14 and 16 as having magical properties in nuclei far from the familiar valley of stability where stable isotopes reside. While new neutron magic numbers were being steadily uncovered, finding new proton magic numbers proved much more difficult, but that changed with a recent breakthrough at the Institute of Modern Physics in China. Scientists there undertook the incredibly challenging task of precisely measuring the mass of SiLiCon-22, an extremely neutron-deficient and short-lived nucleus. Their work was guided by a concept called nuclear mirror symmetry. The theory predicted that if the neutron number 14 is magic in the nucleus of OXYGEN-22, then the proton number 14 should also be magic in its mirror nucleus, silicon-22. After a heroic experimental effort, they successfully measured silicon-22's mass and confirmed the prediction. Proton number 14 is a new magic number. This discovery added a new chapter to the nuclear spellbook, showing that the rules of stability are being rewritten for both protons and neutrons. These surprising discoveries have sent theorists back to the drawing board. The classic nuclear shell model, so successful for stable nuclei, simply can't explain why magic numbers appear and disappear in the exotic realm. To do that, physicists need more sophisticated frameworks, particularly those built from the ground up, known as ab initio or first principles calculations. These cutting-edge theories, which often require staggering amounts of supercomputing power, start with the fundamental interactions between individual protons and neutrons, and build up to describe the properties of the entire nucleus. This work has revealed the crucial role of forces that were often overlooked in simpler models, namely the tensor force and three nucleon forces. The tensor force is a component of the nuclear force that depends on the spin of the interacting nucleons. It turns out that this force can powerfully attract or repel certain pairs of nucleons, changing the spacing between the energy levels in the nuclear shells. In some nuclei, it can push shells apart, creating a new magic number. In others, it can pull them closer together, erasing a traditional magic number. It's a key ingredient in explaining the evolution of the shell structure. Similarly, physicists now understand that three nucleon forces, that is, forces that involve the simultaneous interaction of three particles, not just two, are absolutely essential. For years, models struggled to explain why the oxygen isotopes become unstable after oxygen-24. Why couldn't they hold any more neutrons? The old models, which didn't include three nucleon forces, predicted that the doubly magic oxygen-28 should be the limit. But when these more complex forces were included in ab initio calculations, they correctly predicted that the limit, or neutron drip line, is at OXY-GEN-24, matching experimental reality perfectly. It's the first microscopic explanation for this long-standing anomaly. This beautiful synergy between daring experiments and advanced theory is what's driving the revolution in nuclear physics. So why does redrawing the map of the atomic nucleus matter to anyone outside a physics lab? The implications are huge, reaching from the hearts of exploding stars to our quest to create new elements right here on Earth. First, let's look to the cosmos. The creation of elements in the universe, a process called nucleosynthesis, depends entirely on the properties of atomic nuclei. About half of all the elements heavier than iron are forged in the R process, or rapid neutron capture process. This happens in the most extreme environments imaginable, like the spectacular collision of two neutron stars. In these events, atomic nuclei are bombarded with a torrential flood of neutrons, forcing them to grow rapidly and venturing deep into the territory of the exotic, neutron-rich isotopes we've been discussing. The path of the R process, which elements are created and in what abundance, is directly controlled by the stability of the nuclei it encounters. A magic number acts like a roadblock, where nuclei accumulate before decaying. If the locations of these magic numbers shift, the entire outcome of the R process changes. A more accurate map of nuclear stability is therefore essential to correctly model how the universe cooked up the gold in our jewelry and the uranium in our power plants. Second, this new understanding directly impacts the search for superheavy elements. For decades, physicists have been chasing the island of stability, a hypothetical region on the chart of nuclides where superheavy elements with new magic numbers of protons and neutrons are predicted to exist, granting them much longer half-lives than the fleeting superheavy elements we've created so far. The original predictions for this island were centered around the classic magic numbers, suggesting a doubly magic nucleus near 114 protons and 184 neutrons. But now we know the rules can change. The evolution of shell structure suggests the island might be located somewhere else entirely, or it might have a different shape than we thought. This new physics provides a much more refined map for experimentalists as they navigate the treacherous seas at the top of the periodic table, guiding their quest to synthesize elements with properties unlike anything we've ever seen. In conclusion, the field of nuclear physics is in the middle of a profound transformation. The simple, static picture of magic numbers as unchanging pillars of stability has been replaced by a dynamic, intricate, and far more fascinating reality. Through a powerful combination of groundbreaking experiments at the limits of technology and sophisticated theories that harness immense computational power, we are uncovering a new set of rules that govern the heart of the atom. This journey is not just redefining a fundamental concept in physics, it's giving us a deeper appreciation for the complex and beautiful forces that shape our universe, from the elements in our bodies to the stars in the sky. The map of the nuclear world is being redrawn before our eyes, and the journey promises a future filled with even more magical revelations. Thanks for listening to G Fun Facts Online.